These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the annotation. Thank you. So what we've been doing so far is I've been drawing the electron pushing arrows for you and asking you to draw the product based on those electron pushing arrows. And that's a very crucial skill in OChem, which is why we spent quite a bit of time on it. But now it's time to move on to an even more crucial skill. As you know, in OChem, usually you're not going to be given the electron pushing arrows. Usually you have to come up with the electron pushing arrows yourself. So that's the next topic we have to move on to. The next topic is, how can you figure out on your own what the reasonable electron pushing arrows are? How can you figure out what the correct or reasonable electron pushing arrows to draw are? That's probably the most important skill in organic chemistry, maybe the hardest skill. That's something, in a way, that's what the whole OChem class is about. So we're not going to be able to finish that in just a couple of sessions, but we can kind of sketch the general principles. And then as you go, you start to learn more and more. So in a way, the whole OChem class is about learning how to draw reasonable electron pushing arrows. But there are some general principles that we can go over that can often give us a head start for knowing what the reasonable electron pushing arrows are to draw. So we can start talking about that now. Okay, so let's see. First of all, what is the most important factor in organic chemistry?
The charges.
So, if you're trying to figure out what would be reasonable electron pushing arrows to draw, what's the most important factor to use in drawing your electron pushing arrows?
The charges.
That's right. So that's what we're going to start by focusing on. Whenever possible, you want to use the charges. Now, there's a couple of different types of charges in organic chemistry, but what we've been focusing on so far are what are called formal charges. We've been focusing on what are called formal charges. So we're going to continue to do that now. How can you tell what the formal charges are on a molecule? How can you tell what the formal charges are? Well, first of all, usually the formal charges will already be drawn in for you in the starting materials. Usually the formal charges will already be drawn in for you. So if an atom has a negative charge, you know its formal charge is negative. And if an atom has a positive charge, you know its formal charge is positive. And if an atom is drawn with no formal charge, you know it has no formal charge. There is one exception, though. There's one type of formal charge that you're expected to draw in yourself, and that is in ionic bonds. And you're expected to recognize ionic bonds on your own and draw in those on your own. So what are the types of ionic bonds that you're likely to see in OChem? Does an ionic bond occur between a nonmetal and a nonmetal, or between a metal and a nonmetal?
A metal and a nonmetal.
That's right. When are you most likely to get an ionic bond? When you use things that are separated in the periodic table or close to each other in the periodic table?
Separated.
Because that means that there's a big difference in how much they want electrons. So the most common place to get ionic bonds is when we use metals from the first column of the periodic table. Metals from the first column of the periodic table. In fact, I think you and I have mentioned the three important metals already from the first column. What are the three key metals from the first column of the periodic table?
Lithium, sodium, and potassium.
Yeah. So the point is that when you see lithium, sodium, or potassium bonded to a nonmetal, that's generally going to be an ionic bond. When you see lithium, or actually it doesn't even have to be a nonmetal, always. When you see lithium, sodium, or potassium bonded with something to the right in the periodic table, that's generally going to be an ionic bond. Okay. How about hydrogen? Hydrogen is in the same column of the periodic table as lithium, sodium, and potassium. Is hydrogen a metal?
No.
No. So even though it's in the same column, it doesn't belong kind of in the same group here. Hydrogen does not usually form ionic bonds with other nonmetals, even though it's in the same column as these. So to give you an example, let's look at these three molecules. So is this bond ionic or covalent? Well, this bond is covalent because it's been between bromine and carbon, two things on the right of the periodic table. And is this bond ionic or covalent? Well, this is also covalent because it's between bromine and hydrogen. Even though hydrogen is in the first column of the periodic table, it behaves like a nonmetal, which would be to the right in the periodic table. So this is also covalent. On the other hand, we just said that when you're bonded to sodium, that's going to be an ionic bond. So the important thing is, what is the formal charge on this bromine? Since this is ionic, the formal charge is negative, and we have to draw that in if it's not drawn for us. And we could say this is positive. On the other hand, what's the formal charge on this bromine? Well, since it's covalently bonded, we can assume it has zero formal charge, since the formal charge was not already drawn in for us. And again here, since this is covalently bonded, the formal charge would have been drawn in for us if there was one. Okay, so this is an example here. The key thing is, even if the sodium bromide was originally drawn like this, it would be your job to put in the charges. Remember, the most important factor in organic chemistry is the charges, so we need to know what the charges are. Okay?
Okay.
All right, so what's the formal charges on these atoms?
Zero. Neutral.
They're all neutral. If there had been formal charges, they would have been drawn for you.
Yeah.
What are the formal charges on these atoms?
Potassium has a positive charge, or fluorine has a negative charge.
I just said that if there's formal charges, they would be drawn for you, but this is the one exception. In an ionic bond, the charges are not drawn for you. You're expected to draw them in yourself. Good. What are the formal charges in this molecule?
There are no formal charges. It's neutral.
Yeah, the formal charges would be drawn in for you because these are covalently bonded if they were there.
Yeah.
What are the formal charges in this molecule?
Just a positive one charge on chlorine.
How do you know? Well, it was pretty obvious because it was given to you, right? So as I was saying, when things are covalently bonded, if there's a formal charge, it'll already be drawn for you. So here the formal charge was already drawn for us, so we knew that there was a positive charge on this chlorine. Okay, good.
Yeah.
Good. Okay, do I need to write in any formal charges here?
Yeah, you have sodium on there, so sodium should have a positive charge. And the carbon would have a negative charge.
That's correct. Good. Should I write in any formal charges here?
No, it's covalent, so there's not. If it's not already there,
That's right.
It shouldn't have a.
And should I write in any formal charges here?
No.
Okay, excellent. That's right. Should I write in any formal charges here?
Nope.
No. Good. Should I write in any formal charges here?
Yeah, potassium would have a positive charge, and oxygen would have a negative charge.
Excellent. Good. Should I write in any formal charges here?
No, there's already one there that don't need to write any more in.
That's right. Good. Should I write any formal charges in here?
Nope.
How about here?
Yep. Potassium would have a positive, and oxygen would have a negative.
Good. Okay, good. So that was our first little topic here. So remember, the most important factor in drawing the arrows is the charges, especially the formal charges. How do you know what the formal charges are? Well, usually formal charges will be drawn in for you. However, for ionic bonds, you're expected to draw the charges in yourself. So this is important. Whenever you see an ionic bond, from now on, you should immediately draw in the charges. From now on, for the rest of our careers in organic chemistry, whenever we see something ionically bonded, if the charges are not already drawn for us, we should draw them in ourselves. Okay, good. All right, so now we have to start trying to figure out the rules for how to draw reasonable electron-pushing arrows. Okay, so I'd like you to draw the product based on this arrow.
Okay. Yeah, I guess I'm not sure where the charges would end up with oxygen and carbon.
Okay, well, remember that we had just finished going over the idea that there's rules for drawing for changing the charges. Remember that if we're simply supposed to follow the rules for how to change the charges. So how would you apply the rules here? We're not, in a sense, we're not supposed to have to figure out the charges. We're just supposed to apply those same mechanical rules we've been applying before. So what would happen if we continued to apply the same mechanical rules here?
Well, oxygen would not have any charge changed, but carbon looks like it would have a -2 charge. And I guess that is where I'm confused, because normally we would not want a -2 charge.
Okay, so how? Let's start with the oxygen. How did you think about the oxygen?
It had an electron pair, and it formed I guess it would become positive, formed a sigma bond with the carbon.
So it actually becomes positive. Yes, that's right. Now, it sounds like you might be overthinking that a little. Remember that we want to use the skills that we were just going over previously. All you have to say to yourself is the oxygen is at the beginning of the chain of arrows, so it should become one step less negative. We don't really have to count the lone pairs or the bonds, remember. If you start at the beginning of the chain of arrows, you should become one step less negative. And then, according to the arrows, what would be the new charge on the carbon?
-2.
Okay, so let's go ahead and draw that in. Good, because it started negative and it gained electrons. So remember, we need to draw what the arrows tell us to draw. We're not supposed to be drawing what feels good or what we expect. Now, what would this mean, though? As you know, so does nature like or dislike charges?
Dislike.
Does it want charges to be big or small?
Small.
So is it going to want a -2 charge?
No.
No. So what have we discovered? Well, you've drawn the charges correctly. What we've discovered is this is a bad arrow. We probably made a mistake drawing this arrow. This is not a reasonable electron pushing arrow. Because remember, that's our goal now. Our goal is to learn ways to evaluate when are electron pushing arrows reasonable and when are they not reasonable. Okay,
Yeah.
so the important thing, though, is that you would never even realize that this wasn't reasonable unless you realize that with this arrow you would get a -2 charge. So it's important to realize, so what does it mean if the arrows tell you you're going to get a -2 charge? What does it mean if the arrows tell you you're going to get a -2 charge? It means we need to draw different arrows. This arrow really would give us a -2 charge, but that just means the arrow was a poorly drawn arrow. All the examples I gave you previously, I was drawing reasonable arrows. But now here I drew an unreasonable arrow because that's our next job. From now on, you can't just trust the arrows I'm giving you. Now we have to start evaluating whether the arrows are reasonable or not. So this arrow, it turns out, is not reasonable. So for your notes, you might want to write down, this arrow is not reasonable.
Okay.
How do we know it's not reasonable? Because it gave us a -2 charge. As you were kind of hinting earlier, we should never get a -2 charge in OChem. There's some problems in general chemistry where you get -2 charges, but I don't think there's any examples in organic chemistry, or hardly any examples in organic chemistry where we would get a -2 charge. Okay, I'll go back to my screen. By the way, how did you even know we were going to get a negative charge? I didn't draw a -2 charge. I didn't draw that this started with a negative charge. You had to realize it was because it was ionic. Since this was ionic,
Sure.
you knew it started with a negative charge. So you can see how a student might get this. Why would a student draw this? A student might draw this if they didn't realize this was an ionic bond and they didn't realize the carbon was starting with a negative charge.
Yeah.
If you haven't drawn the negative charge in yet in this picture, it's not as obvious that this is not reasonable. Okay. So let's draw the product based on this arrow.
Okay.
Okay, good. All right, that's right. The oxygen started positive and it's losing electrons, so it became even more positive. So does this look like a reasonable arrow?
No.
No. How can we tell?
It puts a +2 charge, especially, but
Yeah.
it actually adds more charges.
Yeah,
than
it created charges, but the most important thing is it created the +2. So you should never or almost never get a +2 charge in organic chemistry. That's almost always a sign we made a mistake. So again, we can make a note, this is not a reasonable arrow. If you were given this arrow, then the way you've drawn the products would be correct. But then we should say the arrow was not reasonable in the first place. So we can mark again, this is not a reasonable arrow. It would indicate that we'd made a mistake. Not a mistake drawing the product, but a mistake in drawing the arrows. Good.
Oh.
So, what's the lesson here? What's the lesson from these examples? I'll go back to my screen. So, should our chain of arrows, should negative charges go at the beginning or the end of the chain of arrows? Should negative charges go at the beginning or the end of the chain of arrows?
Beginning.
If you put a negative charge at the end of the chain of arrows, like here, you're going to get a -2 charge, which is never reasonable. And should positive charges go at the beginning or the end of a chain of arrows?
At the end of the chain.
Good. If you put a positive charge at the beginning of the chain of arrows like here, it would end up becoming positive 2. By the way, this arrow I just drew here, this is a very common student mistake. Students very often draw this arrow, even though it doesn't make any sense, because they think this is what a deprotonation looks like. It's very common in organic chemistry for things to deprotonate, and this oxygen really does need to deprotonate. This oxygen does need to deprotonate. And so students very commonly draw this arrow. They think this is the arrow that shows deprotonation, but that can't be right, because this would give us a positive 2 charge. So this is actually, hopefully we can see that this is not reasonable, but it's a mistake that students make all the time. Okay, so the rule is, when possible, put a negative at the beginning of the chain of arrows and a positive at the end of the chain of arrows. This is our first rule. Our first rule. When possible, put a negative at the beginning of the chain of arrows and a positive at the end. Another part of this rule that we haven't quite mentioned yet here is you should almost always include the atoms with charges in the reaction. The atoms with charges are the ones that want to participate in the reaction. So if there's an atom with a charge, it's usually going to participate in the reaction. It shouldn't just be off to the side doing nothing. Now, I'll mention right off the bat that there are some exceptions. To this rule. One exception we've already seen. Remember that metals with positive charges are spectator ions. The most common examples. What are the most common examples of metals with positive charges that we've seen that are spectator ions?
Lithium, sodium, and potassium.
So, do we usually put these at the end of a chain of arrows?
Do we usually put those at the end of the chain of arrows? No.
Because they're just spectators. So yeah. Do you see how this is an exception? Normally an atom with a positive charge would go at the end of the chain of arrows, but not these spectator ions. These just don't participate.
Yeah.
Another type of exception is when there are two formal charges. In the same molecule, when there are two atoms with formal charges in the same molecule. Only one of the atoms will usually participate in the reaction. So one of the atoms with a formal charge will not go at the beginning or the end of the chain of arrows. That would be another exception. And then there's also some other exceptions. That maybe we'll see later. So this is a rule that does have quite a few exceptions. What I'm saying here is that when possible, atoms with charges will participate in the reaction. But there are some exceptions. There are a number of times where atoms with charges do not participate in the reaction. So this is a rule, kind of a leaky rule. It does have some exceptions, but it's still a useful rule. Okay?
Okay.
So, are these reasonable electron pushing arrows for these reagents? So this example I'm going to do for you. These are not reasonable. And here's why. Do any of these atoms have formal charges?
Yeah, oxygen next to the sodium does.
But remember we said that when possible, you want to put the atom with a negative charge at the beginning of the chain of arrows. And we didn't do that here. This oxygen was not at the beginning of the arrows. It's just here like a spectator. Well, that doesn't make sense. Do atoms with charges usually act like spectators? No, except for these metals. Normally the atoms with charges are going to participate in the reaction. So these arrows do not seem very reasonable because they're not using this atom with the charge. Okay, so these arrows are not reasonable. Because it would be better to put the tail on this negative charge and draw something that involves this atom here with the negative charge. Okay, so these arrows do not seem, so that's something that might not have been clear here. So the point is, when possible, use the atoms with the charges in your reaction. When possible, use the atoms with the charges in your reaction. Okay? So are these arrows reasonable?
No, I think there should be the negative charge on the first oxygen having the chain of arrows begin with that negative charge.
Good. So these are not reasonable. Now, a lot of students try this, though. A lot of students don't realize these are not reasonable. Maybe one reason for that is because the negative charge wasn't drawn in for you. So remember, your first step would be to draw in the negative charge yourself. So based on the rules that we've talked about so far, do these arrows seem reasonable?
Yeah, they do.
Because now the arrows are starting on a negative charge. Now the arrows are not ending on a positive charge. Why aren't the arrows ending on a positive charge? Well, remember, we only put the arrows ending on a positive charge if possible. Here there are no positive charges for the arrows to end on. Of course, there's a positive charge on the sodium, but we know that sodium is just a spectator ion. So we're only going to put the positive charge at the end or a negative charge at the beginning when it's possible. In this case, that would not have been possible. Okay, good. Are these arrows reasonable?
No.
Why not?
There is a negative charge on the oxygen next to the sodium.
But it's not
So
participating.
the arrow.
Good.
Yeah, it's participating.
Oftentimes students draw these arrows, though, maybe because they don't realize there was a negative charge here because it wasn't drawn in for us. Are these arrows reasonable?
Yes.
Because now the negative charge is at the start. Are these arrows reasonable?
Yes.
Because the negative charge is at the start. Good.
Yeah.
Are these arrows reasonable?
No. It does begin with a negative charge, as it should. The arrows do.
Let me change this slightly. Sorry.
Sure, you're fine.
Let's do this instead. So are these arrows reasonable?
No.
Good. Why not?
Because there's a positive charge that should participate in the reaction.
That's right. Why aren't we using this positive charge? When possible, we want to try to use both the negative and the positive charge in the reaction. This doesn't seem reasonable because it would we're not having the arrows end on the positive charge. Usually, there's some exceptions to that, but usually, when possible, we want the arrows to end on the positive charge. So this doesn't seem likely.
Okay.
Do these arrows seem reasonable?
Yes.
Good, because we're starting on the negative charge and ending on the positive charge. Are these arrows reasonable?
No, it does not involve the positive charge.
That's right. It would be better to involve the positive charge. This seems unreasonable. Do these arrows seem reasonable?
Yeah.
Because they start on a negative and end on a positive.
Yeah.
Do these arrows seem reasonable?
Yeah, they do.
Is there a positive charge at the end of the chain of arrows?
Yeah.
Yeah, there is. This is a little tricky. The head of this arrow is not pointing directly to the positive charge, but it's close enough. This atom would still be gaining the electrons from this arrow. So this arrow is still pointing close enough to this carbon so that it really would be gaining those electrons. So based on the rules that we've talked about so far, these arrows would be reasonable. Good.
Yeah.
Good. Do these arrows seem reasonable?
No.
What's wrong with them?
Well, the negative charge is actually gaining electrons. It's at the end of the arrow chain.
But it's supposed to go at the start, not at the end. Good. So this is completely unreasonable. Electrons don't want to move towards negative charges. They want to move away from negative charges. Good. Is this arrow reasonable?
No, it's not.
How can you see that?
The positive charge has arrows beginning. I guess the arrow chain is beginning at the positive charge, whereas it should be ending at the positive charge.
Absolutely, yes. So this is an unreasonable arrow. Very good. Arrows are supposed to point towards positive charges, not away from positive charges.
Yeah.
Is this a reasonable arrow?
No, the arrows are pointing away from the positive charge.
Good. This is a very common student mistake. Students draw this arrow all the time, even though it doesn't make any sense. Because again, they think this oxygen does need to deprotonate, but this is not the right way to draw the arrow for a deprotonation. But students very commonly draw this arrow for a deprotonation. But this is not what a deprotonation looks like. This doesn't make sense because this shows electrons moving away from the positive charge. That doesn't make sense. Okay, good.
Yeah.
Are these arrows reasonable?
Yeah.
Because in this case, the arrows are starting on the negative charge. Why are we not using this positive charge?
It's a spectator ion.
This is the one a positive charge that's not used because it's a spectator ion. Good. Is this arrow reasonable?
No.
Why not?
It looks well. It looks like the arrow is going toward the hydrogen, which appears to have a negative charge because it's associating with the positively charged sodium.
Okay, good. I don't think I've drawn this example before of NaH, but because sodium is a metal and hydrogen is a nonmetal, we would expect there to be a negative charge here, and we know it's not reasonable for arrows to point towards negative charges. So that's good that you saw that here. So this is unreasonable. This is why it's always important to draw in formal charges in ionic bonds. We have to draw in that formal charge to see that that arrow is unreasonable. Good.
Okay.
Are these arrows reasonable?
I think not. I think that the arrow should end on the positive rather than ending away from the positive.
Okay, good. This is a little different from any of the examples we did before, but this is an extension of that rule we were talking about before. Where are positive charges supposed to go in the chain of arrows?
At the end?
Right. So are they supposed to go in the middle?
No.
No. It's useless to put the positive charge in the middle. Because remember, do we want to keep the positive charge or change it?
We want to change it.
Get rid of it. Well, what would be the new charge if we did use these arrows? If we did use these arrows, what would be the new charge on the oxygen in the product?
It'd be the same.
Yeah, it wouldn't get rid of the positive charge. So generally speaking, we don't put charges in the middle of the arrows. This is unreasonable, but that's that's implied by what we said before, but we haven't quite spelled it out before, so you might want to write that down in your notes. That's implied in this rule here. This implies don't put charges in the middle of the arrows. There are one or two exceptions to that, but generally, when possible, do not put the charges in the middle of the chain of arrows. Do not put the charges in the middle of the chain of arrows. Put them at the beginning or the end, depending on whether they're negative or positive. Okay, good. So that's good that you saw that here. So do these arrows seem reasonable?
Yeah, they do.
Based on the rules we've talked about so far, they seem reasonable. Notice how this is the same example as before, I just shifted the arrows around. So these arrows should be rejected. These look like more likely arrows. These are more likely arrows for this example. Because now the charges are at the beginning and the end of the chain of arrows.
Yeah.
Good. Are these arrows reasonable?
No.
And why not?
The chain of arrows should end on the positive, and the positive charge should not be in the middle of the chain of arrows.
Right. These don't seem right because we shouldn't have a charge in the middle of the arrows.
Yeah.
So how could we fix this? Well, would this be reasonable?
Yeah.
Now, we've changed the arrows so the positive charge is at the end rather than in the middle. So based on what we've seen so far, these seem like reasonable arrows. Good. Do these arrows seem reasonable?
No. The negative charge is in the middle of the chain of arrows rather than at the beginning.
Yeah, we generally want to put the negative charge at the beginning. Here it's in the middle, so this would not get rid of the charge. We don't want to put charges in the middle of the arrows. We want to put them at the beginning or the end of the chain of arrows. Good.
Yeah.
Does this arrow seem reasonable?
Yeah, it seems reasonable. There is no negative charge for the arrows to begin at, and it does end at the positive charge.
That's a good way to think about it. Yes, it would be better if we could start with a negative charge, but there doesn't seem to be one around. At least we're ending with the positive charge. So that does seem like a reasonable arrow. So that's why I said in the rule here, put the negative at the beginning when possible. When possible. If there is no negative formal charge anywhere, then you can't put a negative charge at the beginning. So
Yeah.
those are reasonable arrows. Good. Do these arrows seem reasonable?
Yeah.
There's a negative at the beginning and a positive at the end. Good. Do these arrows seem reasonable?
Well, iron is not one of the common metals that we disregard, so it seems like that should actually participate in the reaction and be at the beginning of the chain of arrows since it has a negative charge.
Okay. Now, it wouldn't really matter whether the iron was in that list or not, because remember the metals that we disregard are metal cations, not metal anions, right? The metals that we've been disregarding as spectator ions are metals with positive charges. Okay, now this one's a little tricky because here I wanted to use this exception that we haven't mentioned in a while. When there are two atoms with charges in the same molecule, you can usually only use one of them in the reaction anyway. When there are two atoms with formal charges in the same molecule, usually only one of them can participate in the reaction. Notice here there's two atoms with formal charges. There's generally no way to get both of them to participate in the same reaction. Therefore, these are reasonable. This is the first time I've given you an example of that exception before. Now, these are not the only possible arrows. You might try to draw a different set of arrows where you used this negative charge and didn't use this positive charge. It's not really obvious which way to do it. So one thing to notice is we're not really for sure saying that all of these arrows, even when we say arrows are reasonable so far, we're not necessarily saying they're correct, so to speak, or the best arrows. We're just saying that they fit with the rules we've seen so far. So based on what we've seen so far, these arrows are reasonable. Although based on what we've seen so far, it would also be reasonable to use the negative charge on the iron and not use the positive charge on the bromine. But anyway, these are reasonable. You can't expect to use both charges from the same molecule. That's what I meant by this exception. This is the first time we've seen an example of that. If there's two atoms with charges in the same molecule, generally only one will participate in the reaction. So these are actually reasonable arrows. Okay?
Oh.
Are these arrows reasonable?
Yeah.
Why is it okay that we're not using this positive charge?
Because there are two charges in that molecule, and we just use one of them.
That's right. So this is the exception we were just talking about. You can't expect to use two charges from the same molecule. Now, it seems like, based on what we've seen so far, maybe it would also be reasonable not to use the negative charge, but to use the positive charge instead. Based on what we've talked about so far, you can't really figure out which one is better. But at least we can say this is consistent with the rules we've seen so far. This is reasonable. We can't expect to use two charges from the same molecule. So that was what the point of this exception is here. All right.
Yeah.
By the way, there are some other exceptions again. There are other cases where you don't use atoms with charges. I don't think I'm going to go over those with you today. They just come up as you're studying particular cases in organic chemistry. So as you go through organic chemistry, you will learn a bunch of other times where you don't use an atom with a charge in the reaction. So this is a rule that has a fair number of exceptions. It's not an iron rule, but it's still it usually works. So it's a useful starting point. Okay. Does this seem like reasonable arrows?
Yeah, it does.
Now, is the negative charge at the beginning of the chain of arrows? It's a little bit trickier here because the tail is not on the atom with the negative charge, but it's close enough. This atom can be losing the electrons from this arrow. The tail of the arrow is close enough to show that it's losing the electrons. So this is reasonable.
Yeah.
Good. How would we interpret this tail? It's between the boron and the hydrogen. So should we interpret this as saying the boron is forming a bond to carbon-2, or that the hydrogen is forming the bond to carbon-2?
The hydrogen.
That way the boron will lose its negative charge. Okay.
Yeah.
Let's see. Okay, very good. All right, so I think we've made some good progress on that rule. This is the most important rule for drawing reasonable arrows. Hopefully this seems obvious, but it's amazing how often students don't use this when they're drawing reactions. When possible, put a negative charge at the beginning of the chain of arrows and a positive charge at the end of the chain of arrows. And notice this has some implications that might not be obvious. For example, one implication is you should use the atoms with charges. This is not reasonable because it's not using this atom with the charge. So one of the implications here is use the atoms that have charges in the reaction, unless they're these spectator ions. And then another implication here that might not be obvious is don't put charges in the middle of the arrows. Don't put charges in the middle of the arrows. You want them to go at the beginning and at the end. Obviously, don't put a negative at the end of the arrows. And obviously, don't put a positive at the beginning of the arrows. That should be obvious, but it's amazing how often students actually do that. Okay, so I think we've made some progress on that. So let's go on to another rule for figuring out whether our electron-pushing arrows are reasonable or not. Let's see. I'm not actually going to draw the atom in here, but so one of these sets of arrows is reasonable and one is unreasonable. Which one makes sense and which one is bad?
The one on the left makes sense. The one on the right does not.
Why is this unreasonable?
Because they are not in a sequence. They're not in a chain. They
That's right.
are coming from two different places. Yeah.
But why is it bad for them not to be in a chain? What's wrong with these arrows?
Well, it's showing electrons moving from two different sources. That wouldn't happen in a single step.
Why not? We haven't seen any examples of that, but there's no particular reason why that couldn't happen. We haven't quite put our finger on why this is unreasonable and this is better.
Whatever molecule they're coming to would not be able to add so many electrons to it.
Okay, that's a better answer. We can be even more, put our finger on even more, though, if we say, what's the most important factor in organic chemistry?
Charge.
So we should be trying to use that. Does nature want charge to accumulate or not to build up?
Not build up.
Is this atom, so this atom is going to be gaining electrons from this arrow. Is it going to be building up a charge then?
No, because it's losing from the next arrow.
That's right. So these arrows are reasonable because they prevent charge from accumulating. What would happen to this atom? Is its charge going to accumulate?
Yeah.
Yeah. If it started off neutral, it would end up with maybe a -2 charge. And even if it started positive, it would end up with a -1 charge. So that's the best reason why this is unreasonable, is because it allows charge to accumulate. If something is gaining electrons from one source, it usually wants to lose electrons to another source. It doesn't want to gain electrons from two directions, because then charge would accumulate. Okay, so we hadn't quite explained that before. So this is a good example of, remember, what's the most important factor in organic chemistry?
Charges.
So if you're trying to explain something, what's the most important factor to use?
The charges.
The charges. I don't think we were quite doing that here. So we weren't quite using the idea of charge to explain why this was unreasonable and this was reasonable. So whenever possible in OChem, the first thing you should be thinking about is what's the effect on the charges. The first thing you should think about in OChem is what's the effect on the charges. Now, I'm not saying that's the only factor in organic chemistry. Remember, we haven't said that's the only factor. Sometimes the charges don't explain things, but that's the first thing we should think about. Okay? Are these arrows reasonable or unreasonable?
Unreasonable.
And why is that?
Positive. Positive charge would accumulate.
Yeah, we'd be accumulating maybe a +2 charge here. This is losing electrons from one arrow. If you're losing electrons from one arrow, you're not going to want to lose more electrons from the other arrow. That would accumulate a positive charge.
Yeah.
Do these arrows seem reasonable or unreasonable?
Reasonable.
So, you said before this seems more reasonable because it's a chain of arrows. But now we can see why we want a chain of arrows. We want a chain of consistent arrows because that prevents charge from accumulating. Okay, so that's why we usually have a chain of arrows. So the head of one arrow will always point to the tail of another arrow. You never have two heads pointing towards each other or two tails pointing away from each other, because that would allow accumulation of charge. So are these arrows reasonable or unreasonable?
Unreasonable.
How can you tell that?
There are two chains. A positive charge would accumulate. +2 charge would accumulate on the oxygen atom.
Yeah, it's not a chain of arrows. Arrows are moving away from the oxygen in two different directions. That seems unreasonable. If you actually drew the product here, you'd have a +2 charge on the oxygen, which we want to avoid. Very good. Okay, so let's try to fix that. Let's do the same example, but draw it this way instead. Are these arrows reasonable or unreasonable?
Still unreasonable.
What's wrong with these arrows?
They are accumulating a negative charge on the hydrogen atom.
That's right. So we don't want to have two heads pointing to the same atom. Now we'd have a -2 charge on the hydrogen. So let's try again and see if we can fix those arrows. Are these arrows reasonable or unreasonable?
Reasonable.
And why is that? Well, they just satisfy all the rules we've talked about. But wait, we didn't put the tail on a negative charge and the head on a positive charge. If we're not going from negative to positive, how can this be reasonable?
There were no charges.
Yeah, can't do it if there are none. That's right. So remember, we're only going to put a negative at the beginning and a positive at the end when that's possible. In this particular example, nobody had any formal charges, so we couldn't put a negative at the start and a positive at the end. But at least these arrows are consistent with each other. The hydrogen is gaining from the first arrow, but losing from the second arrow. Okay, good. Okay, so that's another rule. I think that's clear. So Again, we're going over this because I oftentimes see students do this. Oftentimes students draw these types of unreasonable arrows, but the only types of arrows that are reasonable are this type and this type. Okay, good.
Yeah.
Okay. Now, the next topic we have to go over before we can move on, now we have to go over how can you tell when an atom has a complete octet? Remember that atoms generally that have a complete octet don't have room for more electrons. How can you tell if something has a complete octet? Well, actually, almost everything you see in organic chemistry will have a complete octet. Almost all the atoms that you see in organic chemistry will have a complete octet. So rather than writing down all the ways to have a complete octet, maybe it would be better just to write down the ways to have an incomplete octet. Well, there's only one major example. There's only one major example in organic chemistry of an atom with an incomplete octet, which is a carbon with a positive charge. This is the only major example in organic chemistry that comes up frequently of an atom with an incomplete octet. A carbon with a positive charge has an incomplete octet. By the way, what do we call an atom with a positive charge? Is that a cation or an anion?
Cation.
So what does the word cation mean?
An atom with a positive charge.
Good. And what does the word anion mean?
An atom with a negative charge.
That's right. Sometimes we apply these words to molecules, sometimes to atoms. Good. How can you remember that? It looks like you're already remembering that, but maybe you've seen this memory aid. We could imagine that the T in cation stands for a positive sign. Notice how the T looks like a positive. So this looks like a positive ion. So that's one way to remember it. And then here you can imagine that the N stands for the word negative. So you can imagine that this means a negative ion. So those are some memory aids for these. A negative ion, a positive ion. Looks like you already had that memorized. So what would be the name for this?
The cation.
Good. Now there's a special name for carbons with positive charges. Do you know what the special name is for a carbon with a positive charge?
Carbocation.
Yeah. So what's the one major type of situation? What's the one major type of atom that has an incomplete octet in organic chemistry?
Hydrogen.
Oh, I was going for this one. Carbon.
Oh, okay.
The one major example is a carbon. Although that's actually an interesting example. I wasn't thinking of that, but that's a good point. Maybe I should say there's two examples. So we'll come back to that in a second. I'd forgotten about that, but that's an excellent point. That's important. So what's the one major example that we're talking about here of an atom with of an atom that has an incomplete octet?
Carbon.
That's right.
Carbocations.
Carbocations. All right. What's the difference between a carbocation and just a cation?
A carbocation is a carbon with a positive charge.
And a cation is just anything with a positive charge. Okay, good. Now that you mentioned it, actually I realized I'd left something out. You're right. Another thing that has kind of an incomplete octet is a hydrogen with a positive charge. This is what's called a carbocation. And this is what's called sometimes just a proton. Now, technically, this is not an incomplete octet. This is what's called an incomplete doublet. Because remember, hydrogen doesn't want an octet, it wants a doublet. It only wants 2 electrons, but it's still incomplete. There's still room for more electrons. I had forgotten about that, but that was good that you mentioned that. So maybe these should go together. This is an incomplete octet, this is an incomplete doublet. So these are the only 2 examples, the major 2 examples in OChem of atoms that have room for more electrons. Okay, good. So who goes in this column? Who are the atoms with complete octets? Well, almost everything else. So let's say we have a neutral carbon. Is that complete octet or incomplete?
Complete.
How about a neutral nitrogen?
It's also complete.
How about a neutral oxygen?
Also complete.
We said pretty much everything else is complete. A halogen
Yeah.
would be complete. How about a neutral hydrogen?
Yeah, also complete.
Yeah,
Well,
for example,
complete.
here would be a neutral hydrogen. It has a complete doublet.
Yeah.
How about a carbon with a negative charge?
No, that has more than a complete octet.
Now, that would be impossible, wouldn't it? You can't have more than a complete octet. Generally, you're not allowed to have more than a complete octet. So actually, this still goes in the same situation. This is still a complete octet. This is still a complete octet. It does have a negative charge. By the way this would happen, it would be if you have a carbon with 3 bonds and a lone pair. A carbon with 3 bonds and a lone pair has a negative formal charge, but it still has a complete octet. Because remember, how many electrons do we count from each bond?
2.
So there would be 2, 4, 6, and then 8. So it would still be a complete octet.
I see.
How about a nitrogen with a negative charge? Would that have room for more electrons?
No, it would be complete.
Still a complete octet. So again, almost everything except these two has no room for more electrons. Hydrogen with a negative charge is a complete doublet. How about a nitrogen with a positive charge? That is still a complete octet. These are the ones that are surprising. So does a positive charge guarantee that you have room for more electrons?
No.
No. It only means you have room for more electrons on a carbon or a hydrogen. This is something that might be surprising. These do not have room for more electrons. They have complete octets, even though they have positive charges. Only carbons and hydrogens with positive charges have incomplete octets or doublets. Okay. There is one more example of things that have incomplete octets. These are a little less important, but a metal or a semi-metal with no formal charge would also have an incomplete octet. For example, is aluminum a metal or a non-metal?
Metal.
You kind of know from common sense that aluminum is a metal. Aluminum, so neutral aluminum actually has an incomplete octet, even though it's neutral. Neutral aluminum has an incomplete octet. You can kind of see that. You have your periodic table with you? Notice the aluminum is towards the left in the periodic table, so it doesn't start with that many electrons. Even when it's neutral, it has an incomplete octet. Another example would be boron. Boron is from the same column as aluminum. It's a semi-metal. Another example is iron. These come up sometimes in OChem. These are not nearly as important as these two. But these, so neutral aluminum, boron, or iron, those also have incomplete octets, although that's not as important as this example. Okay. Do any atoms in this molecule have incomplete octets or doublets?
No.
No.
They're all complete.
Do any atoms here have an incomplete octet?
Yeah, the carbon with the carbocation.
Do any atoms here have incomplete octets?
No.
Not even the oxygen?
Not even the oxygen.
Yeah, even the positive charge. A positive charge does not give this an incomplete octet. Do any atoms here have an incomplete octet?
Aluminum does.
Yeah, because it's a metal. Neutral metals do have incomplete octets.
Yes.
So now we're ready for another rule for deciding whether electron-pushing arrows are reasonable. Okay, so here's the rule. Tell me when you have that written down.
Okay.
Does this rule should make sense. Since you have a complete octet, there's no room to gain a bond unless you lose a bond at the same time.
Yeah.
So to give you an example, would you agree this arrow is not reasonable? Whoops. This arrow is not reasonable. What's wrong with this arrow?
That carbon that's gaining electrons needs to simultaneously lose a bond.
So this is not reasonable because there's no room to gain this bond without losing a bond. Maybe we shouldn't call this unreasonable. This is not just unreasonable, this is impossible, or impossible, maybe we should say.
Yeah.
When the arrows are unreasonable, unreasonable arrows don't show things that never happen, they just show things that happen very rarely. Remember that what's really happening in chemistry is you have billions and billions of molecules randomly bumping into each other in your beaker. So almost anything will happen occasionally. Even if something is unreasonable, that doesn't mean it never happens. It just means that it happens rarely in your beaker, so it doesn't give you an important product. But this is something that would happen almost never. This is close to an impossible reaction. So this is maybe a little even worse than being an unreasonable arrow. All right. On the other hand, would you agree these arrows now are reasonable and possible?
Yeah.
Now, here's something tricky. So, how is it okay? Does this arrow show that we're forming a bond?
Yes.
To carbon 3. But carbon 3 had an octet. How is it okay for carbon 3 to form a new bond?
It simultaneously loses a bond.
That's right, from this arrow. But what about the chlorine?
Yeah.
Does the chlorine have a complete octet?
Yeah.
So why is it okay for it to be at the head of the arrow? Well, this is a little bit tricky. It's because, does this arrow form a new bond?
No.
No. So notice this only applies when you're gaining a bond. It doesn't apply when you're... What this arrow really shows is that the chlorine is gaining a new lone pair. You can never break the octet rule by gaining a new lone pair. That's never a problem. Because the chlorine already was kind of sharing the electrons already in the bond. These electrons were already being included as part of the chlorine's electrons in the bond. So in this picture, technically, the chlorine has 6 electrons in the lone pairs and 2 in the bond. In the product, it's just going to have 8 electrons as lone pairs. But either way, it has 8 electrons around it. Here there's 6 lone pairs and 2 in the bond, and here there's just 8 in the lone pairs. Either way, it hasn't broken the octet rule. So you can't break the octet rule by just gaining a lone pair. The only way to break the octet rule is by gaining a bond. That's a little bit of a subtle issue here. So this is reasonable. So does this bromine start with a complete octet?
Yeah.
Yes. But this is still reasonable, even though the bromine is not losing any electrons from another arrow because it's not gaining a bond. Remember, it's okay. So this is another example of what I was just talking about. It's okay to gain electrons as a lone pair. The only time you can break the octet rule is when you're gaining electrons as a bond. I haven't quite explained why that is completely. We'll just kind of, to save time, we'll take that on trust a little bit. Just to save time, I'm not going to completely explain why this is the only way to break the octet rule. We'll just memorize this. So this is reasonable. It's okay to gain electrons as a lone pair. That would never break the octet rule. The only time you could break the octet rule is when you're gaining electrons in a bond. Okay, good. So these electrons would be, this would be reasonable.
Yeah.
Now, this carbon 2 here is gaining a bond, and it's not losing any bonds. So how can this be reasonable?
Well, this, I lost your, okay, there's your arrow, sorry. So this is reasonable because it is lacking. It can add more electrons.
So notice it's okay to gain a bond. The only time that you have to worry about gaining a bond is if the atom started with a complete octet, is the point. If you start with an incomplete octet, it's always okay to gain a bond. If you start with an incomplete octet, it's always okay. So the key thing here is this only applies to atoms that started with a complete octet. They're the ones that cannot gain a bond without losing a bond. If you started with an incomplete octet, then obviously there's room for more electrons.
Yeah.
This arrow, though, would be unreasonable. Why is this arrow unreasonable?
Because oxygen already has a complete octet, and so it would need to lose a bond simultaneously.
That's right. Even though it has a positive charge, it still has a complete octet. Remember, we saw that even atoms with positive charges usually have complete octets, except for carbon and hydrogen.
Yeah.
Good. Okay. Okay. So is this reasonable or unreasonable?
Unreasonable.
Right, or maybe we could say impossible. And why is it impossible?
Yeah. Because carbon next to the iodine is full. It already has a complete octet.
That's right. So how could we fix that arrow?
Have that bond break with iodine, and iodine take the electrons.
So is this possible?
Yeah.
This does seem reasonable.
Yeah.
Good. This is not the only possible, not necessarily the only possibility based on what we've talked about so far, but that does seem reasonable. Good. Does this seem possible?
No. That carbon already has a complete octet. It would need to lose a bond, and it could either lose a pi bond with the oxygen or a sigma bond with the chlorine to make that reasonable.
Excellent. That's a good analysis. How do you know which one to do? How do you know which one to do? Well, so far, you don't know. You'd have to study that later on. This is a reaction you'll study later in the second semester. Later in the second semester, you'll learn that this is what actually happens. That we can't see why this is best based on what we've seen both so far, but we can at least say, does this seem possible?
Yeah.
Yeah, it does seem possible because now the carbon is both gaining a bond and losing a bond simultaneously. Good. This is a pretty common mistake that people make. A lot of the time, this is what's called a carbonyl. A lot of the time people will attack a carbonyl and they don't realize that they need to make room for that. So we can see you can't attack a carbonyl here unless you're making room for it by breaking the pi bond.
Okay.
Is this possible?
No. Hydrogen already has a complete doublet. So it would need to break a bond with oxygen for that to be possible.
That's right. Good. This is, again, a mistake people make a lot. This is a common mistake. They think that this is what's happening because they know that this base is going to take this proton. But those arrows are not reasonable. And I think you suggested what we could do to fix that. Would these arrows be possible?
Yes.
Good. Is this arrow possible?
Yeah.
Even though this hydrogen is not losing a bond, it's okay for it to gain a bond because we said that H plus was one of the things that has room for more electrons. H plus has an incomplete doublet. H plus has an incomplete doublet, so it can gain a bond without losing a bond. Notice the difference here. Does a neutral hydrogen have room for more electrons?
No.
No, not unless it loses electrons. But does a positive hydrogen have room for more electrons? Yes. So, as always, the most important factor here is the charge. There's a big difference between a neutral hydrogen and a positive hydrogen. Although we've seen that many positive atoms still don't have room for more electrons. Okay, good. Is this arrow reasonable?
No. The oxygen with positive charge on it has a complete octet already. We would need to lose a bond in order for that to be possible.
So yeah, this is not reasonable. The oxygen can't gain a bond unless it's losing a bond. Oxygens with positive charges already have complete octets. Let's see if we can find a way then to fix that arrow. Do these arrows seem reasonable? Whoops. Do these arrows seem reasonable?
No, it doesn't, because the carbon on the carbonyl already has a complete octet as well.
Now, is this carbon gaining a new bond?
Oh, I see. It would be not gaining a bond, it would be breaking a bond, but gaining an electron pair, so it would be okay.
It doesn't break the rule we talked about before. Yeah, so that one we got a little bit confused. Remember that the only time that you can break the octet rule, the only time you have to worry about breaking the octet rule is when you're gaining a bond. You can't break the octet rule by gaining a lone pair. Remember we saw that with this example here. Here's an example where this chlorine is gaining a lone pair, but that doesn't really change the number of electrons around the atom for purposes of counting for the octet rule. So you only have to worry about breaking the octet rule when you're gaining a bond, not when you're gaining a lone pair. So are we going to break the octet rule for this carbon?
No.
So do these arrows seem reasonable?
Yes.
Well, they don't break the octet rule. But remember, we've talked about other rules today as well.
They're creating charges, it appears. That, yeah. It doesn't look very reasonable, but I don't think I have the knowledge to explain why.
Okay. Now, I think you might be forgetting one of the rules we talked about earlier here then. What's the most important factor in organic chemistry?
The charges.
And charges should go, where should positive charges go in the chain of arrows?
Oh yeah, that's right. It should be at the end of the chain of arrows.
Not in the middle. So you were mentioning a second ago that this felt wrong, but you couldn't quite express what was wrong with it. But we have gone over the rule for what's wrong with this. We're not supposed to put positive charges in the middle. All right, so this is where organic chemistry starts to get more difficult. It's easy to apply a rule when you've just talked about it. The hard part is that as we go on, we're going to be piling up more and more and more and more and more rules, so that eventually you have to apply 20 rules at the same time. And then it can be hard to apply them all simultaneously. So this was a rule that we were applying correctly earlier, but now it would be easy to start forgetting it. That's the challenging part of OChem, but that's good. That means we're getting into more challenging material here. So now we've covered enough material that we've covered a bunch of different rules. So we have to start to get in the habit of applying them all. That's why students find this difficult. Students don't find it difficult to remember each rule on its own, but there's so many of them that students have a hard time applying them. Well, that just takes practice. It's just like when you're playing chess. If you learn how the bishop moves, then later if you learn how the rook moves, that won't do you any good if you forgot how the bishop moves. And then if you relearn how the bishop moves, that won't do you any good if you've forgotten how the rook moves. You have to keep them all in your head at the same time. So we have to keep all of these rules in our head at the same time, and that takes practice. So that's something we'll be working on. So this is also unreasonable, not because of the octet rule, but because of something we talked about earlier. You're not supposed to put positive charges in the middle of the arrows. They're supposed to go at the beginning or the end. Okay? So let's try again and see if we can fix this. Would these arrows be reasonable?
No, it would not be reasonable because the oxygen with the positive charge is in the middle of the chain of arrows. I believe the only way to make that reasonable is to have that chain of arrows end on the positively charged oxygen. So you'd have to draw the arrow going from the oxygen with the electron pair, and it would end on the carbonyl, and then a new arrow would break the pi bond between the carbon and the oxygen and end on that oxygen with the positive charge. And that way, that would not disrupt the octet rule, and it would also leave the chain of arrows ending on the positive charge.
That's a good analysis. Excellent. Very good. That was a good way to think that through. We're not breaking the octet rule on this carbon now because it's gaining a bond from this arrow, but it's also losing a bond from this arrow. Good. And we're not breaking the octet rule on the oxygen because the oxygen's not gaining a bond, only a lone pair. Remember, you can't break the octet rule by gaining a lone pair, only by gaining a bond. Excellent. That's good. So you can see, though, that this might be difficult for students. So in particular, I think a lot of students want to draw this. This seems very tempting because they know electrons want to move towards the positive charge, right? Since they know electrons want to move towards the positive charge, a lot of students might be tempted to draw the arrow like this. But we can see this is too simple because it would break the octet rule. Even though this is putting the positive charge at the end, it's too simple because it would break the octet rule. So you found a way to have the arrows move towards the positive charge but not break the octet rule. How about if we tried this? Are these arrows reasonable?
Yeah, they appear to be reasonable.
So you might not have realized that there was really two ways to write down reasonable arrows here. The one that you suggested and this one as well. So which one is really going to happen? Well, remember, in a beaker, many things can happen. So both of these would happen in real life. Sometimes the water will attack this carbon, and sometimes the water will attack this proton. Both of these would happen in real life. You would get a mixture of paths. Which one should you draw? Well, that would depend on the details of the problem. So without more information, we couldn't figure out which of these is better to draw for a particular problem. Both of them are possible. So we need more information about the problem to decide which of these is better for the problem, but both of these are reasonable sets of electron pushing arrows. So it's important to realize sometimes more than one set of arrows is reasonable. Sometimes more than one set of arrows is reasonable, and you need other information from the problem to figure out what the best path is to draw for that problem. Okay, so we're about out of time. So anyway, we've been going over now the more difficult part of OChem. I think we made good progress again on drawing the product based on the arrows. So now we're doing the hard part, which is how to draw reasonable electron-pushing arrows. There's many different rules for that, and we just started going over a couple of the rules. So let's see, what are the rules for that we've covered so far. First of all, before you do anything, you have to assign formal charges. We saw that the first thing you have to do is if there's any ionic bonds, draw in the formal charges. That's your job in organic chemistry. So that's one thing we went over. And then we saw this very important rule. Put negative charges at the beginning of the chain of arrows and positive charges at the end of the chain of arrows. For example, don't put charges in the middle of the chain. Don't put charges in the middle of the chain of arrows. Try to always use the negative and the positive charges in your reaction. This is not reasonable because it's not using this negative charge, for example. Now, remember this rule here, there are many other exceptions we didn't talk about. There are a bunch of exceptions to this rule of putting the negative at the beginning and the positive at the end, and you'll learn those as you go through OChem. So this is a rule that has a number of exceptions, but it's still a useful rule. We wrote down a couple of exceptions. There's other exceptions we didn't talk about. But anyway, this is maybe the most important rule, even though there are some exceptions. When possible, put the negative at the beginning and the positive at the end of the chain of arrows. And then, once we got that down, we started moving on to this next rule, which is don't break the octet rule. Remember, the only time when you're in danger of breaking the octet rule is when you're forming a new bond. So you have to make sure that if you're forming new bond, let's see, where did we put this? If you're forming a new bond, it either has to be with an atom that has room, a carbon with a positive charge or a hydrogen with a positive charge, or if you're forming a new bond on an atom with a complete octet, you have to also simultaneously lose a bond. So that was another new rule that we were going over. Now, so far today, I've still been drawing the arrows for you. I've been drawing the arrows for you, and I've just been asking you whether they're reasonable or not reasonable. The next step for us to take is for you to start drawing the arrows yourself. So we can get into that as we go. As we go on, we'll be doing more problems where you're drawing the arrows and evaluating them yourself. But the first step here is that I've been drawing the arrows and just asking you to see whether they're reasonable or not. And if you can evaluate my arrows, then you'll be able to move on to the next step and start drawing arrows yourself and deciding whether they seem reasonable or unreasonable. Notice that sometimes you have to try a bunch of possibilities before you get something that works. If I asked you to draw reasonable arrows here, you might start with this, but this was unreasonable because it breaks the octet rule. Then you might try this, but this is unreasonable because it puts a positive charge in the middle of the arrows. Then you might try this, but this was unreasonable because it put the positive charge in the middle. You might take a bunch of trial and error before you got these two examples that worked. So that's one of the things that frustrates students about OChem. Sometimes the answer is not obvious and you have to just try things by trial and error. So that's something that we'll start working on more as we go. It's important to carefully review what we just went over. Notice you can see how it's important to review because when we were going over the rule about not putting positive charges in the middle, you were doing fine with that. But then when we combined that with another rule, it was easy to all of a sudden start forgetting it. So it's important to review these so that you can put these rules together. So that even when we have 3 or 4 or 5 or 10 rules that we're applying on the same problem, we need to be able to think about all of them. So it's important to go back and review these examples that we went through. I think we were making good progress on them, but it's important to be able to apply all of these rules simultaneously as you go. And let's see, one second. I think there was something else I wanted to mention. Oh, okay. So anyway, what's our goal here? Well, what's the big mistake that students make in OChem? One of the big mistakes students make in OChem is they rely too much on memorization. They think that they're supposed to memorize every single thing that happens in every single reaction. So, in fact, in many cases, you're supposed to be able to figure out what's going to happen in the reaction without relying purely on memorization. So that's what we're focusing on here. We're going over the rules for how to draw reasonable electron-pushing arrows so that you don't have to memorize what the arrows are in every case. You can figure them out if you forget or if you've never seen it before. So that's our goal here. Our goal is to be able to figure out reasonable arrows in a situation so that we don't have to rely purely on memory. And that's important because, first of all, there's just too much material in OChem to rely purely on memory. That just doesn't work. We need to give some help to our memory by understanding the arrows. It's also important, though, because most OChem professors will purposely put problems on exams that are different than they've talked about in lecture because they're trying to force you to figure stuff out and not just rely on memory. So we need this not just as an aid to our memory, but also because your OChem class is generally going to force you to do this, because sometimes there'll be problems on the test that just have new problems you haven't seen before, so that the instructor can force you to rely on understanding and not rely just on memory. So for both of those reasons, it's very important to be able to come up with reasonable electron-pushing arrows on our own. So that we don't need to rely as much on our memory and we can understand more stuff. And so if we forget what happens in a reaction, we can figure it out again by drawing reasonable electron-pushing arrows. So we'll keep working on that.